Welcome to the Audio SoC SDK training. Today I will introduce the information about I/O. I will introduce from the following three aspects: introduction of PAD&Pinmux, introduction of peripheral drivers, and introduction of DLPS. Now, let's talk about the PAD&Pinmux. PINmux is an abbreviation of pin multiplexing, because the SoC has a limited number of pins. Pin multiplexing allows the SoC to use the limited pins for various functions, such as SPI, I2C, and GPIO. PAD is used to control the behaviors of a pin such as pull up or pull down, output high or low level, and wake up functions. As shown in the figure below, PINmux circuit and I/O modules are in the core domain and will be powered down during low power mode, so they cannot work during low power mode. PAD circuit is in the AON domain and will not be powered down during low power mode, so PAD can work normally during low power mode. PAD is mainly used to maintain pin output state or wake up the system in low power mode. Next, I will introduce some peripherals and how to use their API. The following table shows the header file names for some peripherals. The following figure shows the initialization flowchart of the peripheral. Most peripherals can be initialized following this process. Call the RCC perif clock CMD function to turn on the clock of the corresponding I/O module. Then call the PINmux config function to set the PINmux and call the PAD config function to set the PAD. Next, call the init function of the corresponding I/O module to configure the parameters of the I/O module. And finally call the CMD function of the corresponding I/O module to enable the I/O module. PINmux config is used to configure the function of the specified pin. The first parameter is the pin number, such as P24. The second parameter is the pin function, such as UART 0TX. RCC perif clock CMD is used to turn on or off the clock of the corresponding I/O module. Each I/O module has a struct init function that can initialize the parameters of the I/O module to default values. Before calling the init function, you can call this function to initialize the structure variables of the I/O module to default values, then modify the structure variable members according to user requirements, and finally use the init function to initialize the I/O module. Call NVIC init function to enable IRQ interrupt and set priority. The following takes UART 0 initialization as an example to introduce the specific process of peripheral initialization. First, call the RCC perif clock CMD function to turn on the clock of UART 0. Second, call the PINmux config function to configure P24 and P25 as UART 0TX and UART 0RX. Third, call the PAD config function to configure the pin's working mode, input and output status. Fourth, call the UART struct init function to initialize the UART parameters to default values. Fifth, call the UART init function to initialize UART 0. Sixth, call UART int config to enable UART 0 interrupt. And finally call NVIC init function to enable NVIC interrupt. Next, PAD&Pinmux. The following figure shows the two operation modes of PINmux mode and software mode. Now I will introduce PAD. The PAD can be configured to pull up, pull down, and pull none. Configurable strong pull and weak pull. In AON control mode, the output function can be set. Some pins can be configured with different levels of drive capability. In AON control mode, it can be used as AON GPIO, LED and other functions. PAD config is the API for PAD configuration. The first parameter is pin number, such as P30. The second parameter sets the operation mode of the pin, including software mode and PINmux mode. The third parameter sets the power mode of the pin, including power on and power off. The fourth parameter is used to set the peripheral circuit of the pin, which can be configured as an internal pull-up resistor, internal pull-down resistor, without pull-up resistor or a pull-down resistor. The fifth parameter sets whether the pin outputs the level in the software mode. The sixth parameter sets the level value of the pin output in software mode. The fifth and sixth parameters are only valid in software mode. Next, I will introduce GPIO. GPIO supports three modes: output mode, input mode and interrupt mode. All common pins support GPIO function. In the interrupt mode, the debounce time for edge-triggered interrupt can be configured. It supports rising edge, falling edge and double edge triggered interrupts. Also it supports GPIO plus GDMA plus timer function. When using this function, you need to configure GPIO in hardware mode. The following is the initialization process of GPIO. First, call the RCC Peripheral clock CMD function to turn on the GPIO clock. Second, call the PINMux config function to configure P21 and P22 as GPIO functions. Third, call the PAD&Config function to configure the working mode and input or output status of the pin. Next, set the parameters of GPIO. GPIO mode is used to set the input and output mode. GPIO ITCMD is used to enable or disable the GPIO interrupt. GPIO IT trigger is used to set the interrupt trigger type. GPIO IT polarity is used to set the interrupt trigger polarity. GPIO IT debounce is used to enable or disable the debounce function. GPIO debounce time is used to set the debounce time. Then call GPIO-X init to initialize GPIO. Call GPIO-X int config to enable GPIO interrupts. GPIO-X read input data bit and GPIO-X read input data API can read the input level of GPIO. GPIO-X reset bits is used to set the specified GPIO output low level. GPIO-X set bits is used to set the specified GPIO output high level. GPIO-X write bit and GPIO-X write can set the GPIO output low level or high level. In order to use GPIO more conveniently, it is recommended to use the HAL GPIO API. Below is an example of GPIO in output mode. First, call HAL GPIO init to enable GPIO clock. Call HAL GPIO init pin to initialize a pin to GPIO output mode. Then call HAL GPIO set level to set the pin output level. Below is an example of GPIO in interrupt mode. First, call HAL GPIO init to enable GPIO clock. Second, call HAL GPIO int init to initialize GPIO interrupt mode. Third, call HAL GPIO set debounce time to set the debounce time. Fourth, call HAL GPIO init pin to initialize a pin to GPIO input mode. Fifth, call HAL GPIO setup IRQ to set GPIO interrupt mode parameters. Sixth, call HAL GPIO register ISR callback to register callback function. Last, call HAL GPIO IRQ enable to enable the interrupt of the pin. Below is an example of GPIO in input mode. First, call HAL GPIO init to enable GPIO clock. Call HAL GPIO init pin to initialize a pin to GPIO input mode. Then call HAL GPIO get input level to get the pin input level. Next, I will introduce I2C. I2C supports standard mode and fast mode and high-speed mode. Master mode and slave mode are supported. SDA and SCL need to be pulled up strongly. The following is an example of I2C master mode. First, configure the parameters of I2C. I2C clock speed is used to set the transmission speed of I2C. I2C devive mode is used to set the mode of I2C. I2C address mode is used to set the addressing mode. I2C slave address is used to set the slave address. I2C ACK is used to enable the acknowledge mode, and then call the I2C init function initialize I2C. Call I2C-CMD to enable I2C. Call the I2C master write API when transmitting in master mode. Call the I2C master read API when reading. The I2C repeat read API can be called to implement write before read in I2C master mode. The following table lists the interrupts of I2C. The following table lists the status flags of I2C. The following is an example of using interrupts in I2C master mode. First, call I2C int config to open the corresponding interrupt during the I2C initialization process, and then call I2C get int status in the interrupt function to determine whether the corresponding interrupt occurs. If an interrupt occurs, call I2C clear int pending bit to clear the interrupt flag. The following is an example of using interrupts in I2C master mode. First, call I2C int config to open the corresponding interrupt during the I2C initialization process, and then call I2C get int status in the interrupt function to determine whether the corresponding interrupt occurs. If an interrupt occurs, call I2C clear int pending bit to clear the interrupt flag. The following is an example of interrupt usage in slave mode. The interrupt processing flow in slave mode is the same as that in master mode. Next, let's talk about UART. UART supports boot rate calibration, and the maximum boot rate it can reach is 4M. It supports automatic hardware flow control. The RX pin must be pull-up. It supports 7 or 8 data bits and 1 or 2 stop bits. The TX FIFO size is 16 bytes, and the RX FIFO size is 32 bytes. It supports RX timeout mechanism and RX idle timeout interrupt. RX trigger level can be configured from 1 to 29. The FIFO level during transfer can be obtained. The following is the UART initialization process. First, turn on the UART clock and call PINMux config and PAD&Pinmux to configure the TX and RX pins. If the hardware flow control feature is enabled, 2 pins need to be configured as CTS and RTS. Then call UART struct init to initialize the UART structure variable, call UART init to initialize the UART, and call UART int config to enable the UART interrupt. The following is an example of UART sending data in polling mode. Since the size of the Texas FIFO is 16, you can call the UART send data function to send 16 bytes of data each time, and then call the UART get flag state function to check whether the Texas FIFO is empty and confirm whether the transmission is completed. The following is an example of receiving data using interrupt mode. First, the UART RX-related interrupts need to be enabled during the initialization of the UART. In the interrupt function, call UART get IID to obtain the interrupt ID, and then judge which interrupt has occurred according to the obtained interrupt ID. UART int ID RX level reached indicates that the data in the RX FIFO has reached the set RX trigger level. UART int ID RX TMEOUT indicates that an RX timeout occurred. UART int ID line status indicates that a transmission error occurred. You can call UART get RX FIFO len in the UART int ID RX level reach and UART int ID RX TMEOUT interrupts to get the number of bytes in the RX FIFO, and then call UART receive data to read the data in the RX FIFO. The timeout interrupt is triggered when there is at least 1 character in the FIFO, but no characters are inputted to or read from the FIFO during the last 4 characters. If the idle interrupt is enabled, in the interrupt function, first call UART get flag state to determine whether the idle interrupt occurs. If an idle interrupt occurs, first call UART int config to disable the idle interrupt, then clear the idle interrupt flag, and finally enable the idle interrupt again. The idle interrupt is triggered when no data is received and sent within the specified time. When the UART is initialized, the boot rate of the UART can be adjusted by setting DIV, OVSR, and OVSR-ADJ. Next, I will introduce the usage of GDMA. All channels of GDMA support multi-block transfers, scatter-gather transfer, reading current transferred number when GDMA enable, suspend and resume. Configurable GDMA channel priority. Call the function GDMA channel request to request an unused DMA channel. GDMA channel num is used to set the channel number of GDMA. GDMA dir is used to set the transfer direction and can be configured as memory to memory, memory to peripheral, peripheral to memory, and peripheral to peripheral. GDMA source data size is used to configure the transfer data width of each source transfer. GDMA destination data size is used to configure the transfer data width of each destination transfer. GDMA source M size is used to configure the number of data items read from the source each time a source burst transaction request is issued, and the width of each data item is GDMA source data size. GDMA destination M size is used to configure the number of data items to be written to the destination each time a destination burst transaction request is issued, and the width of each data item is GDMA destination data size. Last, GDMA buffer size is used to configure the amount of data to complete a GDMA transfer. An example of GDMA is as follows. First, set the parameters of GDMA, then call GDMA init function to initialize GDMA and call GDMA CMD function to enable GDMA. Call GDMA int config function to enable GDMA transfer completion interrupt. When the GDMA transfer is complete, the transfer complete interrupt is triggered. In the interrupt function, the interrupt flag bit needs to be cleared first. Call function GDMA safe suspend to suspend DMA channel. Timer and PWM. Timer has two operation modes, user-defined count mode and free running mode. The width of timer is 32 bits. Support clock frequency division. Each timer supports PWM output. Timer 2 and Timer 3 support dead zone output. It supports emergency stop control. Below is an example of timer usage. First, call HWTimer create to create a timer based on the specified parameters. Then call HWTimer start to start the timer. When the timer count reaches 0, the timer interrupt will be triggered. In the interrupt function, the callback function is executed. Below is an example of PWM usage. First, call PWM create to create a PWM based on the specified parameters. Then call PWM pin config to configure PWM output pin. Last, call PWM start to start the PWM. Below is an example of dead zone usage. First, call PWM create to create a PWM based on the specified parameters. And call PWM config to configure dead zone parameters. Then call PWM pin config to configure PWM output pin. Last, call PWM start to start the PWM. Capacitance touch. Next, I will introduce CapTouch. The capacitive touch controller uses a single pin and measures the capacitance between the capacitive sensor pin and ground. The capacitive touch controller uses changes in capacitance to detect the presence of a finger on or near a touch surface. As shown in the figure below, the sensor parasitic capacitance is called CP. When fingers touch or approach the sensor's surface, it forms a simple parallel plate capacitor with the sensor pad through the overlay. The result is called finger capacitance CF, and it increases the measured capacitance CS. In the initial state, an amount of charge is built up on an untouched sensor to set the sensor's reference level, CS equals CP. As the finger makes contact with the sensor, it couples with the electric field of the sensor. This results in a drop of that sensor's charge since a portion of that charge is drained off through the finger to ground. Further charge transfers from that sensor result in a reduced signal level compared to the untouched state. CapTouch have 4 channels. When the sensitivity is 5 UA, the sampling range is 5 to 45 picofarads, support finger touch and proximity detection, configurable sensitivity, adjustable baseline and touch threshold, programmable scan period. CTC will scan automatically according to the scan period. It supports the etc. function, which automatically initializes baseline and automatically updates baseline and threshold in different noise environment. CapTouch can adjust the ambient noise threshold, support 2 touch judgment modes, and support debounce function and interrupt control. The pin of CTC channels 0 to 4 are P00, P01, P02, and P03 respectively. The schematic diagram of CapTouch detection is shown in the figure below. CapTouch use the ADC on the IC to collect raw data. CapTouch have P noise threshold, N noise threshold, baseline and touch threshold. Touch threshold is divided into difference threshold and absolute threshold. When the etc. function is enabled, the difference threshold is used to judge the touch state. After the ADC collects the raw data, it will average the data, subtract the average data from the baseline to obtain the difference data, and compare the difference data with the difference threshold. If the difference data is greater than the difference threshold, it will be judged as touch. If the etc. function is turned off, the absolute threshold will be used to judge the touch state. After the ADC collect the raw data, it will average the data and compare the average data with the absolute threshold. If the average data is less than the absolute threshold, it will be judged as touch. CapTouch has P noise threshold and N noise threshold. When the difference between the raw data and the baseline is greater than P noise threshold, CapTouch send P noise interrupt to the host, and the host needs to initialize the baseline. CapTouch sends N noise interrupt to the host when the difference between baseline and raw data is greater than the N noise threshold. The following figure is the initialization process of CapTouch. The following figure is the interrupt handle flow of CapTouch. The following is an example of the initialization flow of CapTouch. First, call CapTouch system enable to enable CapTouch function. And call CapTouch size reset to reset CapTouch system and clear all settings. Then call CapTouch CHCMD to enable specified channel. Call CapTouch CHIntConfig and CapTouch noiseIntConfig to enable CapTouch interrupts. Call CapTouch set scan interval to set scan interval. Call CapTouch CMD to start CapTouch. The following is an example of interrupt handle flow. First, call CapTouch getIntStatus to get the interrupt status. Then call CapTouch as CHInt triggered and CapTouch as noiseInt triggered to check interrupt status flag. If the interrupt status flag is set, call CapTouch CHInt clear pending bit and CapTouch noiseInt clear pending bit to clear interrupt. Please refer to SDK document for other peripheral. Next, I will introduce DLPS. All used register values will be saved on area RAM before entering DLPS. All used register values will be restored after exiting DLPS. Support check DLPS wake up reason. Support check power down wake up reason. The IO-DLPS register enters CB and IO-DLPS register exits CB API, are used to register callback function that need to be executed when entering DLPS and exiting DLPS respectively. The pad control select value function is called to switch the pad to software mode when entering DLPS, and to switch the pad back to PINMUX mode when exiting DLPS. Call function DLPS utils print wakeup info to print DLPS wakeup reason. Call function powerdown check wakeup reason to check powerdown wakeup reason. Thank you.